section 4.1, we're going to look at base functions, where we have like exponential curves, things that are growing, doubling, or tripling. So we're going to look at different bases raised to different powers. The first thing is just learning how to use our calculator to do this. So if I have 4 raised to the 2.4, you have to type this in your calculator like 4, and then there's a button on the cheaper, or I should say less expensive calculators that will look like an up arrow like this. And then you type 2.4 and you hit enter. Depending on your calculator, this might be y to the x, this button. It might be, I've seen somewhere have x with a little box like that. So you have to find the button on your calculator, and you can Google your type of calculator and say exponents, and it will tell you. And once you do this, you will get the decimal value 27.8576 approximately. And then it wants us to round to 3 decimals. So a quick review on rounding. For 3 decimals, we stand on the third number, look to the right. If it's 5 or bigger, we're going to bump that up by 1. So the actual answer we will record is 27.858. And that's number 1. It should be real quick and easy as long as you have practiced your calculator. I encourage you to practice your calculator during the lesson so that during the test you're not fumbling around trying to figure out how to use it. Problem 2 is the same thing. It's base 5 now. So in our calculators we would have to type 5 and then raise 2, but there's a new wrinkle here. It's a negative number. So we want negative 1.4. Now order is going to be important. Some calculators, they want you to type the number and then a minus button to make it negative. So you're going to have to play around with your calculator and see how it wants it. So one way it'll usually give you an error. It'll say syntax error. But if you, so if it didn't work that way, then try a different order and you should be able to get it to work. Now, let's caution you here. So this right here. There's 2 different minus signs on most calculators. There's a subtraction button, which is longer. So this means subtraction. And we don't want that. So we're trying to raise it to a negative power. So look on your calculator, there will be a smaller little minus sign like this. And that is the minus sign you want. Okay, so I've seen people try to use the subtraction key for this, and it will throw an error. So make sure you're looking for a smaller little minus sign. Use that button to make the 1.4 a negative number. And when you hit enter, you should get for this one 0.10506. And they want us to round to 3 decimals again. So stand on the third number, look to the right, it's 4 or smaller, so you just dump everything. So we would say the answer is 0.105. And that's number 2, just more calculator practice. Okay, for number 3, it's yet another button on the calculator. This is the button e to the x. Now, a lot of calculators will hide this above the ln button. So a lot of calculators will look like this. They'll have ln, and then in a different color, say orange, they'll have e to the x above it. Well, to get that, then they'll have a button that has the same color as that. So usually it's called shift. They'll have a button up here on the top of your calculator that says shift, and it will be in the same color. So to get this, you just have to hit this shift key and then hit this ln key. And that will give you the e to the x key. So this e to the x is a natural number. This is the natural number, and it's called the exponential. And it's kind of a famous number, 2.718. So the base is just really 2.718, and you can find that by typing e to the 1 in your calculator. And so this is really approximately 2.718 raised to the negative 0.81. But you don't want to use the approximate number. Use the e key, because that's going to store like 16 numbers to represent the natural number. So you have to find that button on your calculator, type that, and again, order might order is important here. So sometimes they want you to type the number and then this E key. So just see how your calculator wants it. And you also have to get the minus sign for 0.81, enter. So you might have to reverse this order. This is order dependent on calculator. So play around with your calculator, figure out what order it likes, and to know if you got it right, here's the answer. So if you type this incorrectly, you should get 0.44486. And they want us to round to 3 decimals again. So stand on the third number, look to the right, it's bigger than 5, 5 or bigger, so plus that number up by 1. So the final answer we would record is this number is approximately 445. When you see equal signs like this that are wavy, these wavy equal signs, this means it's approximately. So, not an exact answer, it depends on how much you round, so it's an approximate number. Okay, that's 3. Okay, in problem 4, we have to do some graphing. So we have the base is 2 raised to the x, and we have negative numbers. I'm actually going to start with 0, and then we're going to form a pattern. So let's say we have f of 0. That would be 2 raised to the 0 power. Anything to the 0 power is 1. So any number raised to the 0 power is 1. So that's something we can record right away. Then we try 1. When x is 1, we get 2 to the 1. Any number to the 1 is itself. So 2 to the 1 is 2. So any number to 1 is itself. And then we try 2. F of 2 would be 2 to the 2, which is 2 squared, which is 4. So we get 4. And what we notice is these numbers are doubling. So if x was 3, we would get 8, and so on. Okay, so they're doubling going this way, or if you go this way, they're halving. So half of 4 is 2, half of 2 is 1. Half of 1 is 1/2. Half of 1/2 is 1/4. But we don't have to necessarily just rely on the pattern. Let me show you that in action here. So if I plug in f of minus 1, that's 2 to the minus 1. So any number, any x raised to a negative power, you can write it as 1 over x to the positive power. So we're going to write this as not 2 to the minus 1, we're going to write it as 1 over 2 to the first. And now 2 to the first, any number to the first power is itself, so that's 1/2. So that's how I got that 1/2 there. Let's try negative 2. It would be 2 to the negative 2, which is the same as 1 over 2 to the positive 2. And 2 squared is 4, so we get 1 over 4. And if we had negative 3 here, it would be 1 over 8. So another way to see it is, these negative numbers are just the reciprocal of the positive numbers. So when x is 1, I get 2. When x is minus 1, I get 1 over 2. When x is 2, I got 4. When x is minus 2, I get 1 over 4. This is another way to see it. Okay, now if you plot these, first off, notice that none of these numbers are negative. So if we have x to the minus n, we get 1 over x to the positive n. So for any n, for any number we pick, 1 over x to the n must be positive. So for this to be negative, I'd have to have a negative number somewhere. I'd have to have a negative in front of the 1 or a negative in front of the x. There's no exponent that can produce a negative number in front of that 1 or that x. In fact, the pattern is even negative x's produce positive numbers. So 1/2 is 0.5, it's positive. 1/4 is 0.25, it's positive. And they're they are getting smaller. 1/8 is 0.125. It's positive, it's getting smaller, closer to 0, but it's still positive. We can immediately eliminate A and C because they have negative numbers. They have negative y values. And then we just have to match it up. So if you look, D is the best answer. So we have, when x is 0, we're 1 unit high. When x is 1, we're 2 units high. When x was 2, we had 4. When x is 3, we would have gotten 8, so it'd be up here. And so it just keeps going. And then over here you get 1/2, and this is approximately 1/4. So that would be what the picture looks like. And what's going to happen is, and we'll see this a lot today, this line is going to continue to flatten out, and it's going to approach the line y equal to 0. That's called a horizontal asymptote, which we've seen before. So it has this flattening out where the function will approach 0, but it will never be 0, and it will never go negative. Okay, so a lot more there, but that's pretty much the gist of all the rest of the problems we're going to do. So if we get 4, we should be able to do the next one fairly quickly. Okay, 5 is the reciprocal of 4. So 4 was base 2, 5 is base 1/2. So let's see what happens with this one. In fact, let's start with the negative numbers. When f is negative 2, we get 1/2 x to the minus 2. We're going to do the same thing. We're going to change this to positive by flipping the fraction. So we're going to flip the fraction, call it 2 over 1, and we're going to make this positive. So we can change this to positive by flipping this. Flip that fraction. And 2 over 1 is just 2 raised to the positive 2, which is 4. Let's try negative 1. It would be 1/2 to the negative 1, which we're going to flip the fraction, call it positive 1, which is 2 to the 1, which is 2. Let's try 0. Well, I just got done writing. Any number to the 0 power is 1, so this is 1. And at this point, we can pretty much stop and look at the pattern. So to get from 4 to 2, they halved it, the same base. The base is halved, so these numbers will be halved. So half of 4 is 2, half of 2 is 1, half of 1 is 1/2, half of a half is 1/4. And so notice again, no negative numbers. So no negatives. So we can eliminate graphs C and D because they dip into the negative realm for y values. Not going to have that. And it looks like the best answer is going to be A. So let's match it up. When x is 0, we're at 1. When x is minus 1, we're at 2. When x is minus 2, we're at 4. So these A matches up perfectly. And then we have half, and then we have 1/4. Okay, so when we flip the base, it kind of reverses this. So in the last one, it grew as it went left to right, and this one, it's shrinking as it went left to right. In fact, let me overlay that. So the last one we just looked at was 2 to the x, and it looked like this. This was 2 to the x, and this blue one is 1/2 to the x. So notice how they're doing two different things. One's going up, one's flattening out towards 0. In fact, let's put that in also. This is also going to flatten out at y equal to 0. Okay, so that's 5. Okay, in problem 6, they want us to use the same base function, 2 to the x, and then they want us to do 2 graphs, one with that, and then one where we just transform that graph. So we're going to save ourselves time if we remember our transformations, our graph transformations. Let's review what x and 2 to the x was, though. So let's pick some x's. And if you remember the pattern on 2 to the x, they double. So 0 is 1, At 1 it doubles to 2, then it doubles to 4, then it doubles to 8. And the left side is just 1 over each of these numbers. So minus 1 is 1 over 2, and minus 2 is 1 over 4, and minus 3 is 1 over 8. And we can quickly graph this. At 3, negative 3, you're at about an eighth, barely above the x-axis. At negative 2, you're at a quarter. At negative 1, we're at a half. 0 goes up to 1. 1 goes up to 2. 2 goes up to 4. 3 goes up to 8. And so we get this function that's going to flatten out at y equals 0 up to infinity. So this is 2 to the x. Now with transformations, we can quickly do g of x. So let's do that in green. So if I have negative 4, that is going to shift this 4 to the right. In fact, let's look at all the possible transformations. If it was 2 to the x plus 4, this would be 4 up. If it was 2 to the x minus 4, this would be 4 down. If it's 2 to the x plus 4, so notice the difference here, this is 4 to the right. And then the last one is the one we have, 2 to the x minus 4, is 4 to the left. So these are the 4 translational transformations we would have, up, down, left, or right. And so notice when the number is right up there next to the x in the exponent, it's left or right. If the number is down in line with the 2, it's up or down. Okay, so this is 4 to the right. So all I have to do is count 4 units to the right from each dot. 1, 2, 3, 4. 1, 2, 3, 4. 4. These are a little harder to get. They're 1/4 and 1/8, but they look like that. And if we plot this curve, it is also going to flatten out at y equals 0, and then it's going to grow like this. So this will be 2x minus 4. So the first part says, what is this? Where is this flattening out to? And both of these curves are flattening out towards y equals 0, which is the x-axis. So the asymptote in this one is y equal to 0. What's the domain of the green curve? So the domain, notice, domain is left or right, x values. So going left to right, record the x values. So all the way to the left, this green line is going to go, it's going to keep going over to minus infinity. So notice I'm looking at this from two lenses. When I look at what's it flattening out towards, I'm saying what's the y value, what's the up and down value it's flattening out toward? Well, it's flattening out towards y equals 0. Now when I talk domain, I say left or right. What are the x values doing? These x values are getting bigger and bigger and negative. So it's going to start at negative infinity. What about the right side? So what will it do? So since this curve is angled up and to the right, there's a component of it that goes to the right, to positive infinity in the x, and there's a component that goes up, which would be positive infinity in the y. So we have to consider this from two lenses, left or right, up or down. Okay, in fact, the range values, as you're looking down to up, what are the y values? So notice that there's no y values that are negative. In fact, the drawing doesn't even start until y equals 0, until this x-axis. So the lowest it can be is 0 with a parentheses. So this function will never be 0, but it can get close to 0. And then it's going to go up to that red arrow to positive infinity. Notice that this asymptote and this matched. So that's a theme here. Whatever that asymptote is typically either where the function starts or where the function stops. So that number will either show up first or last with the range. Okay, so that's problem 6. Okay, 7 is going to use 3 to the x as its base. So if we say x, and then the function is now 3 to the x, well, these numbers are just going to triple. let's start at 0. 3 to the 0 is 1. 3 to the 1 is 3. 3 squared is 9. 3 to the third is 27. So notice these numbers are tripling. 1 to 3 is tripled. 3 to 9 is tripled. 9 to 27 is tripled. Now the negative side is 1 over these numbers. So minus 1 would be 1/3. Then it would be 1 over 9. And then it would be 1 over 27. Okay, so starting at negative 3, we're at 1 over 27, which is barely above the x-axis. Then minus 2, we're 1/9, it's still barely above the x-axis. At minus 1, we're 1/3. 0 is 1. At 1, we're 3 units high. At 2, we're 9 units high. And 27 units would be off the chart. So this one is going to look very, very similar to base 2. Going to flatten towards y equals 0 and then go up to infinity. So this is 3 to the x. This one's also approaching y equals 0. Now for the g of x function, this minus 5, because it's not up next to the x, it's going to be up or down. And minuses are down, so this is 5 down. So we just have to count from these dots 5 down. Barely above this line at negative 5. Barely above this line at negative 5. Third above the line at negative 5. This would be negative 4. This would be down here at minus 2. This would be down here at positive 4. So this curve is going to flatten out towards negative 5. Up to infinity. So this would be 3 to the x minus 5. Notice this one flattens out towards the y, the horizontal line, y equal negative 5. So what is the asymptote? It's y equal negative 5. The domain, just like before, this is going to go to the left to minus infinity. This is going to go, it's slanted, so it's going to go up and to the right to positive infinity. So just like before, the domain is all real numbers. The range, the y values as I go down to up, the lowest it is at negative 5. And it's not going to touch it, so nothing's below negative 5. No green is below negative 5. It starts at negative 5, but it'll never touch that line. And then it's going to go up to positive infinity. And notice once again these match. But you have to draw the picture because we're going to see one where the numbers match, but it's not in this first slot, it's in the second slot. So you want to draw the picture and you really analyze it going left to right and then down to up and see where your graph starts and where it goes. Okay, problem 8 is very similar. So we have the base function of 3 to the x, and we can quickly sketch that. So when x was 0, we have 1. At x is 1, we have 3. When x is 2, it's up here at 9. And then it goes to 1/3, 1/9, 1 over 27. So borrow what we just did, flatten out at the x-axis, and go up like this. This is 3 to the x. Now we have two transformations. This says go 1 to the left, and this is 1 to the right. Or excuse me, 1 up. Sorry about that. 1 left, 1 up would be that transformation. What we do is just count from these dots. And it doesn't matter, I can go up and left, or left and up. I'll get to the same spot. So we would have left, 1 up. These are harder to draw down here. Barely above this line, barely above this line. So the new curve would flatten out at 1 and then go up to infinity. So this is the curve, 3x plus 1 plus 1. And notice that this one flattens out at positive 1. and the original one flattened out at y equal to 0. So this one up here, this one up is going to translate to this new asymptote. So it's going to shift that asymptote up 1. So we'd say the asymptote for that is y equal to 1. What's the domain? So just like before, this curve is going to go to the left to minus infinity. It's slanted up here, so it's going to go right to positive infinity. The domain is the same. Any real number will work. How about the range? So the range, as I look bottom to top of the green, it's going to start at 1. So it's going to start at 1, so this again matches. And then it's going to go up to positive infinity. So pretty similar. The curves look very similar. 2 to the x looks like this, 3 to the x looks like this. And we're about to see e to the x, which is in between these two. Very similar. Okay, so this is e to the x. Now let's look at 2 to the x. Let me do 2 to the x in blue. That one started at 1, and then the numbers doubled. So it went to 2, and then it went to 4, and then when x is 3, it goes up to 8. And then over here it halves. So 1/2, 1/4, 1/8. So this thing is going to look like this. That's 2 to the x. Now let me do 3 to the x in green. Still starts at 0, 1, but then it's at 3, and then at 2 it's at 9, and then 3 to the third is off the chart at 27. Over here it's a third, and then a ninth, and then a 27. So this thing's going to come in, cross through the same point there, and then go up. E to the x is the same as 2.718 to the x, approximately. So notice 2.718 is right in between these two. So 2.718, a little closer to 3 than the 2, but it's going to be in between those two curves. So it's actually going to be sandwiched in between these two, cross through the same point 0, 1, go up like this. So this would be e to the x. So very similar curve. It's just going to be in between those two. Okay, but let's actually get some numbers so we can actually plot this. So let's clear this out and use our table and get some actual numbers. And I'll do blue for the parent function, and then they want us to transform it. So let's say we have x, and then our function is e to the x. And I think I picked pretty standard to pick -2, -1, etc. So let's go -2, -1, 0, 1, and 2. And again, you need to find that e key on your calculator. If you find it and plug in -2, you should get 0.135. At -1, it's 0.368. Any number to the 0 is 1. E to the 1 is 2.718. And then e squared is 7.389. So if we plot these, -2.135 is barely above the x-axis. -1.368, that's about a third of the way off. 0, 1. 1, 2.78, about there. And then 2, 7.389, about up here. About like that. A little trickier to do since these numbers aren't whole numbers that sit on a grid mark. So this is e to the x. Now, the transformation in green. They want us to take the negative of e to the x. So let's actually do this, and then we'll figure out what a minus sign in front does. So this minus sign is going to make each of these numbers here negative. So instead of 0.135, we have negative 0.135. Instead of 0.368, we have negative 0.368. And this one's -1, and -2.718, and -1, minus 7.389. So what we're going to have is a dot right here, about a third of the way down, 0, negative 1. At 1 we have negative 2.78, about there. And at 2 we have negative 7.389, about there. And what we have is, so let's see, this one went to 0, approach 0. This one, as we fill it in, also approaches 0, but it approaches it from the bottom, not from the top. So what did that minus sign do? If you look at this, it's a reflection. So it is reflecting, this is reflecting the original curve, e to the x, about the x-axis. So a minus in front of the function will just reflect it like a mirror across the x-axis. Now that is going to affect our domain range, so we have to be careful here. What is the asymptote? Well, the asymptote is still y equals 0, so it's flattening out at 0. What's the domain? So the domain will still be, it's going to go left to negative infinity. It is slanted, so it's going to go down and to the right, so it's going to go to the positive infinity, so that doesn't change. But now the range, you have to be careful here. You always go bottom to top, so the bottommost value this has is it's going to keep going down to minus infinity. So it actually starts at minus infinity, and now I have to think about the largest this ever is. Well, the largest this ever is 0. It's going to flatten out there. So these match, but notice that in this case it was the second slot. So it's the biggest it can ever be is 0, and it starts at minus infinity. So, that's a good problem. In fact, part of your project is to work with exponential functions. So you'll want to practice with your calculator, and if you can do this problem, you can do part of your project. I encourage you to take a look at that. Okay, for problem 10, we're going to have the base of 1/2. So we have the numbers for that in one of the previous problems, so I'm just going to kind of quickly sketch it in. When x is negative 3, you have 8. Let me do blue for this. I like to do the parent functions in blue. And then we can do the transform ones in green. So minus 3, 8 would be one number. Minus 2, 4. Minus 1, 2. 0 and 1. When x is 1, 1/2 to the 1 is 1/2. When x is 2, 1/2 squared is 1/4. When x is 3, 1/2 to the third is 1/8. 1/8. So we have this function here that is actually halving. So it's getting smaller, but never 0. So it's approaching 0. And now the transformation is just, they want us to shift this 3 to the right. And this would be 5 up. And again, it doesn't matter. I can go 5 up, 3 right, or I can go 3 right, 5 up. Give me the same spot. So let's start here. 3 to the right. 1, 2, 3. 5 up. 1, 2, 3, 4, 5. It's somewhere off the chart. 1, 2, 3. 1, 2, 3, 4, 5. 2, 3. 1, 2, 3, 4, 5. So like this and like this. So this one is going to come up here to infinity, and then it's going to flatten out at y equal to 5. So this one just wants the asymptotes. The asymptote for blue was y equals 0, and the asymptote for green was y equal to 5. And again, that plus 5 up is going to kind of indicate where that asymptote should be. Okay, now we're going to shift gears a little bit. We're going to look at compound interest. So compound interest is you have a base and you raise it to a power, and it depends on, so basically you put your money in a bank or you buy a mutual fund or something like that, and you want to see how your money is going to grow. Or if you take a loan out, how much are you going to have to pay in addition to to how much the loan was because of interest. This depends on a couple things. First, it depends on the principal. So how much did you invest? So in this case, we invested $20,000. So the investment is P. A is the accumulated value. So how much money will I have in the future? The time is T, in this case 4 years. And then the interest rate we record as R, and it gives it as a percentage, but to do the calculation we want to convert that to a decimal. A decimal value. Okay, so principal, interest, time, and then the fourth thing to consider how much money we'll have is compound period. So we have in this case we have 4 different cases. One is compounding semi-annually. Semi-annually is twice per year. So N is 2. And so what happens is, when the bank compounds your money, they assess your money and say, okay, how much interest has your investment earned? And then they award that interest to your account. And then, now, the beauty of that is now your interest is making more interest for you. So if you put $100 in the bank and you earn $5 interest, now the next year you have $105. So now that $5 interest is now also making interest for you. So instead of making $5 the next year, you might make $7. So now you have $112 in the bank. And now that $12 is making interest. And so if I made $7 before, now $112 might earn me $9 interest. So the interest is going up, your balance is going up, and so you get this compounding effect where it's growing faster and faster. Okay, so semi-annually means that they award this interest twice. Quarterly means they award it 4 times. Monthly means they award it 12 times. And you can have daily, 365, and then you can have continuously, where they compound it all the time. Basically, all the time your interest is earning more interest. When you have compounding continuously, you're going to use the E button. So we're going to use the base E, and we're going to use this formula up here. A equals PERT, or PERT. Okay, but for all these other ones, we're going to use this formula here. So we're going to use this one for any n other than infinity. So yeah, this is basically, let's put that. This is basically n is infinity all the time. So we're going to use this one for all n except n equal to infinity. This one is when n is equal to infinity. So continuously, we're going to use that second one. The hardest part about these problems is just getting it in your calculator correctly. So let me give you some setups and then try this and see if you can get the same numbers. If you can't, you can send me a picture of your calculator or explain how you're doing it, and I can explain what you need to do to get it right. So the formula is A is equal to P, which in this problem is 20,000, times 1 plus R. Now this is where you have to convert this to a decimal. So 7% as a decimal, just divide by 100%, would equal 0.07. And then we're dividing by n. N is the compound period. In the first problem, it's 2 for semi-annual. Then we're raising it to n, which is 2, times the number of years, which is 4. And you'll get 20,000. I would work inside out, so take 0.07, divide by 2 in your calculator, get a number, add 1 to that number, it should be 1.035, and then raise that to the 8, which is 2 times 4. Get that number, then multiply that number times 20,000, and if you do that, you should get $26,000, 336.18. Okay, now for the quarterly one, the only thing that changes in the formula is 2 numbers. It's still 20,000, it's still 1 plus 0.07, but now it's divided by 4, because we did it quarterly. And it's not raised to the 2 times 4, it's raised to the 4 times 4. So notice the only 2 numbers that are going to change in this are this number and this number. And if you do this one, you should get 6,398.59. and your homework will want this to the penny, so you don't want to do much rounding here. You want to get to the accurate penny. Okay, then the last one, our future amount is 20,000 times 1 plus that same 0.07, but now it's 12 because it's monthly, and then it's raised to 12 times 4. This one would be 26,441.08. Okay, then the last one uses a different formula. So continuously, we use PERT, principal 20,000, times E, that button on your calculator, raised to the 0.07 times the number of years, which is 4. So you'll have to take 0.07 times 4, use that as the exponent for your E key on your calculator, multiply by 20,000, and you should get 26,462.60. And if you look at these numbers closely, what you will realize is that as your n gets bigger, so as your compounding period increases, the money you get back increases. So there's two things you're looking for to maximize your investment money, and that is the rate you can get and the compound period that they offer. And you want the highest for both of those. That will maximize your investment dollars. Okay, the last problem in this section is going to be a very consumer-friendly one where, okay, I have money, I want to invest it. Where should I take it? Should I take it to Bank A or Bank B? And they offer different amounts and potentially different compound periods. So we have 14,000 invest. That's your principal investment P. We have 1 year, so that's the time. We have one rate that's 6% compounded monthly, so N is 12. Or we have a second rate, let's call this rate 1 and rate 2, compounded continuously, so we're going to use the E formula. So let's find the future amount when we're compounding monthly. So we have 14,000 times 1 plus 6% converted to decimal will be 0.06 divided by the compound period 12, raised to the compound period 12 times the time, which is 1 year. And if you get all of that correct on your calculator, you should get that your 14,000 grows to $14,863.49. So notice your money made you $800 in 1 year and you didn't have to lift a finger to do it. In fact, all you had to do was refrain from spending any of that 14,000, which can be hard to do, I guess. The second one, let's actually use color for this, R2, this uses E. Same principle, 14,000, but now it's times the E key raised to the 0.0592. So notice, smaller interest rate, but they're compounding more often. So which is going to win? The slightly smaller interest rate, which would hurt our money, but they're compounding it more often, which would help our money, times 1 year. And the future amount for this scenario is $14,853.82. And you'll notice that the green one is about $10 more. So the winner would be this one. So we want to compound at that 6% rate. We have slightly increased money when we decide to withdraw. Okay, that will do it for section 4.1.